So today I'm going to talk about our project Glimpse, which is responsible to bring down the power consumption and data transmission for a variable vision system by at least one order. So variable devices are around us anywhere. So we use them for applications like call tracking, to recording video, and also use them in some vision application. Unfortunately, the variable vision system has not been that successful, partly because their camera pipeline, wireless camera pipeline, bears a lot of power, so avoid them from basically lasting for a long period of time on a single charging pattern. So the question is that why camera pipeline bears that much power? The answer is actually simple. So you can see that I have a block diagram that's showing the primary building block of a wireless camera system. It consists of an imager, an image processor that interfaces with the camera and also compresses the video, and also a communication module. The power consumption of each particular block is being given on top, and also the power budget available on the variable battery side is also given in the bottom. So comparing these two numbers, we're talking about more than 2 watts of continuous power consumption on a variable vision system, while what is supplied is only less than 200 millivolts. So we are talking about 10 to 30x in the power gap between what is demanded for variable vision system and what is supplied. So one easy sort of high-level solution to basically bring down the power consumption of variable vision system is to basically have some sensors that can gauge the variable vision system and tell that now something interesting is happening in the field of view. Now you turn on and do your task. So people have done some work in this area. For example, SenseCam and StartupCam are 2 projects that are basically being shown on the left. These 2 projects basically use some low power, low data rate sensors such as motion sensor, gyroscope, and accelerometer to basically trigger when the higher function camera should turn on. But the issue with this sensor is that there are simply a lot of situations that these low power, low data rate sensors cannot detect. For example, assume we are interested in detecting when the weather is interacting with an object or with another element. So it's not clear that how these low power sensors can basically detect properly this situation. Our approach, however, is to gauge vision with vision. That seems like a chicken and egg problem in the first place, but our solution to this approach is Glimpse gating board. Glimpse gating board is responsible to reject uninteresting frames as early as possible in the camera pipeline so that avoid burning too much power. So Glimpse is a total redesign of camera architecture all the way from imagers down to processors and algorithm. So by relaxing the precision of the conventional computer vision algorithm, we're introducing Coarse version of them that bear far less power than the traditional version. So in the following, I'm going to start with the hardware architecture of the system and then go software architecture and give you some example. So Glimpse as a whole system actually consists of 2 main parts. One of them is the Glimpse gating board, which is responsible for rejecting uninteresting frame early, and that is the low power part of the system, and it's basically highlighted in the actual green lines. And also the other part is the high resolution camera that is being triggered by the Glimpse system. Glimpse basically leverages a variety of low power sensors. Including thermal, including accelerometer, gyroscope, and also some imagers, including thermal imager and stereo pair RGB camera. It also has an FPGA, a very low power FPGA that is responsible to perform intense tasks, and also a microcontroller that provides an easily programmable platform for the application developer to basically decide if the scene is interesting or not. Finally, based on the decision that is made on the gating board, a primary imaging system is the high resolution high power system will be triggered, and then that will start recording the imaging system. So basically, to give you an idea how this programming model of Glimpse gating will work, let's focus on the Glimpse software architecture. So down below we have the Glimpse sensor and Glimpse processors. Using these, we have provided some feature calculation libraries that the user can just simply use them and chain them together and come up with some programs that decide on the scene a single output. These programs that the user can basically write, we call them rejection passages. So let me give you an example of a rejection passage. So to the left, we're seeing some sample output of the board or what the user is actually seeing. And on the top, we're seeing the result of a monochrome stereo camera. On the bottom, to the left, we're seeing the thermal camera that segments the body parts from the background. And on the bottom right, we are seeing that those parts of the image that are close enough here is highlighted with red boxes. So a simple cascade can basically be something like the user is interested to detect if the weather is interacting with an object or with an image. So simply, the user can basically first look at the output of the motion calculation library. If there was enough motion and thermal activity in the background, it can basically move on. Otherwise, it would reject the frame right away. If there was enough motion in the field of view, then activate the thermal segmentation, which is this picture that you see in the bottom. Activate the thermal segmentation. Thermal segmentation would look for human body temperature signature. If you didn't find any human body, it would reject the frame right away. Otherwise, it would send the coordinate of a particular segment to the depth estimation system or library. And then they have to check that if the distance of the object is far from the better, and they reject the frame, otherwise it would send the trigger signal to the primary high resolution image. So the important question here is that how to implement the boxes on the right feature. These are our feature calculation libraries. So we have developed a lot of Coarse algorithms that the details of them is in the paper. Here I'm just going to focus on one of our own algorithms, which is Coarse depth calculation. So why do we refer to phrase of Coarse? So the reason is that the traditional, for example, depth estimation algorithms, they provide us depth at every single pixel with very high accuracy. For example, ZCam is an example of a device that has a stereo camera and provides depth at this resolution and at 30 frames per second, but that burns more than 10 watts of power. That's far beyond the budget that we are looking for. But on the other hand, we are basically introducing the Coarse version of all of these algorithms that, first of all, they do not provide depth at every single pixel because we don't need them. They basically require a minimum size of an object, and beyond that, they provide depth. And also, they provide depth in sort of discrete levels of depth, not the actual depth. For example, let's say, is the object within 1 meter or within 1 meter and 2 meter? And is it the object? And is the object at infinity? So, let me briefly explain how the traditional stereo depth calculation works, the algorithm how it works. The problem of extracting depth from stereo camera is a problem of finding correspondence between the left and the right photo. So if you have an object within distance p from stereo camera, and we take the left and right photo and superimpose them in the same image, what we are left with is two copies of the object that would be the star pixels apart from each other. People call it the disparity is the star. If we can find an optimal disparity in the star, we can figure out what's the depth of the object. So we did some optimization on top of that traditional algorithm to bring the power consumption down while we were keeping the accuracy as high as possible. So the first trick that we did was buffer-free implementation version of the algorithm. So traditionally, people store the photos, left and right photos on the RAM, and then after the photos are being stored, then they basically do the process on top of the data and access to RAM to basically extract them. But we know RAM, comparing to accessing registers, for example, in FPGA, accessing RAMs is much more powerful. So we eliminated the need for a buffer by exploiting the fact that FPGAs are designed for parallel computing. So we have a machine that can be used in parallel. So what we have done here is that the pixel stream is coming from both left and right images. So as the pixels are coming in, the FPGA creates different variants of the right image of the imager and basically tries to compare that with the original image coming from the left image. So where this comparison results in this noise value, that's where basically we have found the optimal extraction. Just note that all of these circuits are in delay and the comparison, they're all parallel circuits being implemented on the FPGA. So we want to minimize the size of circuit being taken on the FPGA to reduce the power consumption. So the next trick is that we ask this question, can we, instead of checking every single pixel disparity, can we basically skip some of them and just check the sparse set of them? So the answer is that assuming we have a stereo pair, we put an object at a particular distance from that stereo pair. If the object becomes closer to the camera, first of all, that looks larger in the photo domain. And secondly, the disparity becomes larger. Larger disparity meaning that if we come down from our algorithm pipe, larger disparity meaning that if we come down from our algorithm pipeline, meaning that as the disparity becomes larger, we might be able to basically skip some of these comparison checking. So by doing this trick, we could basically reduce the power consumption of algorithm by more than 60% while picking up only 5 to 7%. So the next trick was that can we truncate the bit representation of pixels and still get the same sort of accuracy? So the two photos that you're seeing here, the one on the left is showing the non-truncated version of a photo. The middle one is a photo that has been truncated by 3 bits, basically 5 bits representation for each pixel. And the last photo is just a single bit black and white sketch photo. So you can see that in human eye, between first and second photo, it's not much difference. So we ask this question, what happens if we feed the truncated version of the images to the FPGA? So the result was that by doing that, we can reduce the power consumption by another 40% while picking up only 15% on accuracy. So actually, it does not end here. There's one more layer of optimization, which is, as I mentioned before, we are only interested in the coarse version of the algorithm. So the actual depth is not important for us. We're just looking, is the depth within a particular kind of discrete level. So by basically quantizing depth to some certain level, we could basically increase the accuracy by 10%. So overall, we could reduce the power consumption of depth calculation by more than 75% and only giving up 10% accuracy. Basically, summarize about to evaluate how our system basically working. Real setting, we did a setup which I'm going to explain before. So I wore that kind of device around my neck, which I'm going to explain what this device is. It actually includes gaining board, which is responsible to detect if something interesting is actually happening in the field of view. It also has 2 Raspberry Pis. One of them is recording video uninterrupted, so all the time. So it's recording from ground truth. Collection, the other Raspberry Pi is being triggered by the Cascade. So whenever something interesting happening, the other Raspberry Pi actually starts recording and upload data through Wi-Fi to a laptop that can be carrying on that laptop. And finally, there is the national consumer data acquisition system that is recording live power consumption data from all of the Raspberry Pis and also from different modules within the Cascade. So I record that system over 3 days and collected more than 15 hours of data while I was doing normal data, something like I was driving, I was having lunch with friends, I was going for a short walk, and a few other scenarios. So the interesting thing is that if you look at the highlighted part there, it's showing that the pass-through rate, or basically how many frames have not been rejected from the system, is actually pretty low. So on average, only 5% of the frame were let through the system, while the maximum was something like 17% when it was happening once, which was expected because it was interacting with people. My hand was coming in and going from one direction, but it's still only 17% let through. If you look at the precision number, they are modest, which is fine. It's the coarse nature of the system that we have modest precision. But what we care more about is the read number. So you can see for the interesting events of 3 seconds, we almost detected all of them properly. And as the interesting event becomes shorter, we basically lose a little bit of each pattern. So finally, I just want to conclude with showing that short video that's showing how the output from the triggered Raspberry Pi. So whenever something interesting happens in the field of view, the triggered Raspberry Pi basically start recording video, and you can see that it is sort of summarized version of the actual. You see a lot of jump, it's because the camera actually turns it off and comes back. And with that, I just want to thank you